Hey, good morning everyone. Back again to videos. You'll notice my shirt this morning. It says on it, a day without math is like, how would I know? Just kidding. I wouldn't know. I've never been a day without math. Well, that might be a wee bit exaggerated since I've only been doing this for about 10 years. But if I think about it, even when I wasn't teaching math, I was using math in daily life. And today we're going to go in more into depth on something that we actually talked about at the end of the last video. If you will remember, we mentioned what was called the empirical rule. So today we're going to go into more detail about the empirical rule, and we're going to cover how to use that empirical rule, and you will have your assignment will use this knowledge. So here we go, the empirical rule, because you actually use this if you think about it. Okay, empirical rule. Remember, the empirical rule is built on what is called the normal curve. We used to call this, when I was first introduced to these concepts, we called this the bell curve. And the bell curve is built on the fact that the majority of the data lies in the middle of the data. And that is exactly where the mean is. The mean, the mode, and the median are the same thing when you look at the bell curve or the normal curve. And the empirical rule says what? Well, your empirical rule says that one standard deviation, I'm going to put SD for standard deviation, to either side of your normal curve, this area contains 68% of the data. So one standard deviation to either side, this area here contains 68% of the data. If we go to the second standard deviation to either side of the bell curve, so that's going to bring you over to here, and these should be equal distance, even though I'm not very good at making them that. So this is the second standard deviation, this much, and that contains 95% of the data. In other words, from here to here contains 68%. From this line all the way to this line contains 95% of the data. And then the third standard deviation on each side this one contains 99.7% of the data. In other words, from this one all the way to here, this part contains 99.7% of the data. That leaves only 0.3% of the data for these two little tiny tails on either side. Therefore, this tail contains 0.15% of the data, and this tail up here contains 0.15% of the data. We can break this down even farther, and we will. But first of all, I want you to understand that, notice your standard deviations are positive. First standard deviation, second standard deviation, third standard deviation. The other thing you need to understand is under this bell curve, or this normal curve, 100% of your data falls underneath that normal curve. And if you were to take an area under the curve, that would be the number 1. And so one of the things we're going to talk about in the next lesson is what happens if you don't land on one of those standard deviations. And we can also use this standard deviation to talk about probability. For example, 68% of the data lies between the first standard deviation on either side. Therefore, if you take a test, you actually have a 68% chance to end up between the first standard deviations on either side of the mean. And we'll talk about the significance of that in a bit. But we're also going to break down this empirical rule a little bit more. If we took this 68%, since there's two equal pieces in it, it means that this piece here is 34% of the data. In other words, half of the 68% fall between the mean and the first standard deviation to the left of the mean, and 34% of the data lies between the mean and the first standard deviation above the mean. That one was easy. All you had to do was take 68 divided by 2 and you got your 34. Now, we want to know how much lies in these two pieces between the first and the second standard deviation. Well, first of all, we need to find out what the total of those two pieces are. And so you will find it by taking 95 minus 68, which is going to equal 27. And then 27 divided by 2 is equal to 13.5. Therefore, this piece right here is 13.5%, and this piece is 13.5% of the data. Now, we want to know what between the second and third on each one of these. So we're again going to subtract the 99.7 minus 95, because it's this one minus this one, and that's going to equal 4.7, and 4.7 divided by 2 will give you 2.35. Therefore, this piece in here is 2.35% from here to here, and 2.35% from here to here. So we have now broken out each little piece of this particular empirical rule or the normal curve, and have applied the empirical rule to it. That gives us information, but what do we do with that information? And this is where its power comes in. Okay, there are 5,000 students. Those 5,000 students took a college algebra test. Okay, a college algebra test. Now, the interesting thing is what happened here. The mean, and I'm going to use the symbol for the mean of the college algebra test is 65%. And the standard deviation of the college algebra test, and I'm going to just use the letter S because that's the most common one used, S for standard deviation. I'm going to put that down so you don't forget it. Standard deviation. My S is equal to 10%. So what do I do with this? Well, the first thing you will do with this in your homework is you will draw a normal curve like I have already drawn. And then you're going to put this information on your normal curve. So my mean is 65%. 10% is my standard deviation. So 65 plus 10 means that the break at the first standard deviation to the right is a 75, and add 10 to that is 85, and so on, making 95. So once I have more than 75 and more, I'm the first standard deviation and above. If I go less than the mean. Now I'm going to subtract my 10, making 55, 45, and 35. Now these are the scores on the test that show where a student lies on this standard deviation. And so you can already see the disadvantage of the standard deviation. Our breakpoints are precise scores, but what was yours? What was your relationship to this whole thing if you fell in between these standard deviations? Next lesson we're going to cover that. We're just going to look at empirical rule on this one. So now we can use this to answer questions about this particular information. So my first question is, between which two values are 68% of the grades found? So we're looking for the values of the test where 68% of the grades lie. So you're looking actually for the values that match the first deviation on either side of the mean. And so therefore 55 to 75. So students who got 55% to 75% were in that first standard deviation. Okay? Now, let's look at the next one. What would be the students that lie between 95%? So if we were looking at values at 95%, what would that be? Well, 95% is second standard deviation, which is 45% to 85%. Now let's look at something else with this. What percent of the grades lie between 45 to 75? Well, this isn't hard to do if you have completely broken it down. What do I have? A 13.5% plus 34 and 34, which would be a 68 plus 13.5% and percent. And that's going to equal a 81.5%. So 81.5% of the student scores lie between 45 and 75. What if I were to ask, what percent of the students lie between 45 and 85? Well, already did that one. That's 95%. What percent of the students did better than 75? Okay, so greater than 75%. So the percent of the students that did better than is a 13.5% plus what? Well, we've got, how about 2.5%? Because this is 2.5 plus 13.5. It's going to give you, carry my 1, 2, 3, 6, 16%. So 16% of the students did better than 75 on their test. Okay? Now another question we can ask ourselves is, how many of those students did between 45 and 85? Okay? Since 95% of the students did between 45 and 85, you're going to take 95% of 5,000, okay? So that will be 0.95 times 5,000, which is going to equal, that's 950 per thousand times 5. 4,750 students. And this is actually students, so you're going to have to label it as such. Okay? Then it says, how many students got between 45 and 75? Well, 45 to 75 is, didn't I do 45 to 75? Yeah, right here. 45 to 75 had 81.5%, so that one's going to be 0.815 times 5,000. Oops, one more zero. And that's going to give me how many students? That's going to give me 4,075 students. And the last question is, how many did better than 75? Well, we can take 5,000 minus 4,075, and we're going to end up with 925, or you can take your 16%, 0.16, times 5,000, and that should give me the same answer. No, 800, really? Well, let me check that out. 13.5, check my math on this. Plus 2.35 plus 0.15. Yeah, that's a 16%, but it should be the same. Oh, I know what's wrong. This one's correct. Why is this one incorrect? Think about it. That 5,000, what did it cover? It didn't cover this part down here. It was from here to here. But we're wanting greater than this. So therefore, we're not looking at simply the subtraction of 5,000 minus the result of this, because we forgot about that part down there. So this is not correct. You have to be careful on things like that. I made a mistake on it. That's okay. Okay, now, what do we do in education with the normal curve? Often when we have many, many students in the same class, and we have these huge numbers of students, used to be psychology was this way. A teacher might have 5,000 or 10,000 psychology students in the same psychology class when I was back in college. And so they would grade the students on a normal curve. And it didn't matter where your score was as far as in relationship to 100% on the test. You could have a 95% on the test and still get a C. Why? Because your grade was in the first deviation to either side of the mean. So this one wouldn't be bad. From here to here, first standard deviation, all of those students would get a C. And you really wouldn't mind that, because usually this would be a D and this would be a D and that would be a C. But you know, those that are had lower scores, they would really like this. And 75 to 85 would be a B, and again, people wouldn't mind that. Greater than 85 would be an A, whereas 45 to 55 would be your D, and less than 55, this would be your F, less than 45. So if that happened to be a normal curve for this college algebra test, most students would be happy with it, because you would get higher scores, you would get higher grades at a lower score. But that's not the way most of these turn out to be. Usually what happens on this is you end up with a mean of 85. And how about a standard deviation of 5? So this would be 90, 95, and 100. Down here you would have 80, 75, and 65. So what happens on this kind? Say this was what you had. You would get a C if you had a grade between 80 and 90. You would get a B if you had between 90 and 95, and an A if you were better than 95. You would get a D between 75 and 80, and an F if you were less than 75. You see the problem with grading on a normal curve. It depends upon what the mean is. If the mean is really high, then you're not going to get high grades unless you're way, way up at the top, because it's not based upon the percentage of the problems correct to the number of problems given. Most of us, we grade on what is called a percentage. In math particularly, we do that. We grade a percentage, and the percentage is based on problems correct over total problems. And so when you do this, you're getting the percentage correct on your test, and that gives you a real score. But when we're talking about the empirical rule, now we're talking about, in a sense, what is called a percentile. And a percentile deals with position in relation to all the scores. And so if people score high on the test, you end up with a lower grade, because your position in relation to the other scores is what we're looking at when we're looking at percentile or the empirical rule. So you can see the pros and cons of that for a test and why it would make it hard. So we can do percentile, which bases position on 1 through 100. In other words, we're going to break it all up into 100 groups. And how does your group relate to the other 100? So you're looking at percentile is position in that list of scores. Another way we do that, we've already mentioned it with the box plot, and that one is called quartiles. So when you're looking at quartiles, which is what the box plot is, you're looking at dividing all the group into fourths. So a quartile is 1/4 of the data. So you're going to break the data up into 4 pieces. And this is, remember, your Q1, your Q2, and the Q3. These are the median. This is the median of all the data. This is the median of the less than Q2 data. And this one is the median of the greater than Q2 data. And so when you're talking quartiles, again, you're talking placement in relationship to all the other data. So less than Q1 has 25% of the data. Less than Q2 has 50% of the data. Less than Q3 has 75% of the data. So you can see that if you look at that, it's just a larger, in a sense, standard deviation. The Q2 would be the median, and it would match the mean. And then the Q1 and the Q3, and then everything less than that. So you can see they really relate to each other. Your empirical rule and your quartiles deal with the same idea. Remember, empirical rule, you had here to here was 68% of the data. Same thing is true if you look at Q2 to Q3. This contains 50% of the data because, remember, each one of these sections is 25%. So you see how these two concepts relate to each other in the way that they function. They are both placing you in relationship to everybody else, okay?